All right, just a quick topic here from section 3 is what we talk about is infinite sequence and series. Infinite means we keep, if it's arithmetic, adding and adding and adding. Well, obviously, if we keep adding a value on and I keep trying to add those numbers, we're never going to get a sum. I mean, that number's just going to keep getting bigger and bigger and bigger. Okay, same way if it was a negative common difference, it's going to keep getting smaller and smaller and smaller as we add them together. With geometric, if you think about an exponential growth situation, again, what happens is these numbers keep getting larger and larger more quickly and quickly. So those numbers, if I keep adding them, are going to keep getting bigger all the time. But if we have a situation in a geometric sequence where my value for r, okay, is less than 1, okay, and we should also throw in here it's got to be greater than 0, okay, we have a situation where it's exponential decay. And so what happens again is we get closer and closer to an asymptote, but we never quite get there. And think about this situation. Again, I use this a lot with exponential decay. Line up on one side of the room. Every time the second hand hits 12, you can go halfway to the door. When you get to the door, okay, you can leave. And again, we talked about how you're never going to get to the door. Okay, you're going to get closer and closer and closer. We're approaching the door. We're getting closer. And that's the idea of when you get into calculus, talk about limits. Okay, you're getting closer and closer to something, but you're not quite getting there. And so if the numbers that I'm adding on each time in this series are getting smaller and smaller and smaller and smaller and almost 0, getting really close to 0, it's almost like I'm adding nothing. And so that's why we're able to deal with a sum for an infinite geometric series. Okay, we're really not going to go into the infinite sequence idea. It's part of the section, but we're just dealing with the infinite geometric series in this case. So one of the things I have to do is, number one, if they say find the sum of this series, okay, one, I have to verify that it is geometric. So I have to look at my ratios, so second divided by first. And secondly, what I have to do is make sure that that ratio is less than 1, absolute value-wise. And so again, if I check my third divided by my second, multiply by my reciprocal, again, I do get negative 1/7. Okay? And so now here's our formula. What I'm doing is I'm taking my first term and divide it by 1 minus r. Okay? So in this case, it's as simple as 21 divided by 1 minus negative 1/7. Okay? So 21, okay, you could use your calculator, but this is going to become addition. 1 is the same as 7 over 7, so what we have is 8 sevenths. Okay? And if I do go to my calculator now, what I'm going to do is 21 divided by, and because it's a fraction in my denominator, put it in parentheses, and we get 18.375. Okay? So if you go back and look at it, I started with 21, took away 3. That got me down to 18. Then I added 3 sevenths. So it got a little bigger, but now I'm going to take away, my next term would be a negative 3/49. So I'm going to take a little bit away, and then I'm going to add a little bit, and I'm going to take away a little bit. And those numbers that I'm adding and subtracting are getting so small, so that's why I'm staying close to that 18. Okay. So same idea here. Find the sum of this series. Well, again, number one, we have to check to make sure it's geometric. Okay. So if I take 2.2 divided by 2, I get 1.1. That's greater than 1. Okay. So therefore, I'm not going to have a sum. Okay. Again, because it's greater than 1, what's happening is every time I add another term into this sequence or into this series, it gets bigger. Okay, so we're not approaching any value. We're going to keep getting bigger and bigger and bigger. And that's as quick and as easy as that section is.